So the next speaker is Renxing Wan at Peking University, and he's going to tell us about uniform exponential growth for groups with a proper product action on hyperbolic spaces. Please start.
Maybe now you can hear me?
Yeah, we can hear you.
Okay. Thank you for the introduction and thank you for the invitation. I'm very glad to give a short talk here. And today I'm going to talk about a classical question in geometry group theory. It's about uniform exponential growth. And we studied this property for a group with a proper product action on finite hyperbolic spaces. And this is joint work with Professor Wenyuan Yang. Okay, let's start. Okay, at first, I'm going to introduce some basic conceptions. The first is the uniform exponential growth. That is giving a finitely generated group G with a finite generating set S, and we consider the closed ball of radius N centered at the identity in the Kelly graph. You can see the ball, and we count how many group elements it has. Then we define the exponential growth rate of G relative to S. It is defined to be the limit, which always exists. And once we have this definition, we can say that a group G is said to have exponential growth if the omega GS is strictly bigger than 1 for some generating set S. And one thing to mention is that if you have two different generating sets, for example, S1 and S2, and if omega G S1 is strictly bigger than 1, then omega G S2 is also strictly bigger than 1. But if we take an infimum over all finite generating sets, then we get a number called omega G. And if the omega G is also strictly bigger than 1, then we say that the group has uniform exponential growth, right? The uniform means that it is uniform for all finite generating sets. And a classical question proposed by Gromov in 1980s is that, is there a finitely generated group which has exponential growth, but no uniform exponential growth? And this question was solved by Wilson in 2004. He constructed an example that has exponential growth, but no uniform exponential. And sometimes we call it a Wilson group now. However, it is still interesting to ask another question. For what kind of groups exponential growth will imply uniform exponential growth? And there are some no results here, including hyperbolic groups, relatively hyperbolic groups, amalgamated free products, and HNN extensions, and one-related groups, mapping class groups, and many hierarchically hyperbolic groups. Okay, and for us, we studied the uniform exponential growth for a group acting properly on a finite product of hyperbolic spaces. And so I'll briefly introduce what is a proper product action. Given some geodesic metric spaces, C of x1 to xl, and we denote x to be the product space with L1 metric. And a group G admits a proper product action on X if G acts properly on the product space X and preserves each factor. And here, notice that we say a proper action. We mean it is metrically proper because the space Xi may not be a proper space, right? So here, a group action is called metrically proper if for any bounded subset, not compact. For for any bounded subset K, the set of group elements that does not move K far away is finite. But briefly, we still call it a proper action. Proper action. Okay, so why do we think about this kind of group action? A typical and original example for us is a kind of groups with property Qt. This conception was proposed by Wenyuan, Bromberg, and Fujiwara. They say that a finitely generated group G has property Qt if it acts isometrically on a finite product of coarsely trace, so that the orbit map is a quasi-isometric embedding. And with a recent result of button, a group with property Qt up to passing to a finite index subgroup has a proper product action on a product of finite coarsely trace. And the coarsely trace are, of course, a Gromov hyperbolic space. And here, another thing to mention is that we always pass to the finite index subgroup. This is okay. Why? Because if finite index subgroup has uniform exponential growth, then the bigger group, the whole group will also have uniform exponential growth. That's a well-known fact, but maybe some people here are not familiar, so I will mention that. Okay, so now I will raise our question. For non-elementary group G with property Qt, whether G has uniform exponential growth, and furthermore, for group G with a proper product, a finite product of hyperbolic spaces, when will G have uniform exponential growth? Here is a remark, an interesting remark, that any finitely generated group will act properly on a proper hyperbolic space. For example, you take the combinatorial horoball over its K-graph, then any finitely generated group will act properly on this proper hyperbolic space. So you need to improve this situation. You hear me? Okay, you hear me? Okay. So you need to exclude this situation, right? Otherwise, any finitely generated group will act properly on a hyperbolic space. That's not what we want. So you need to exclude this situation. And now we use some preliminaries and assumptions that we use. Although we focus on the product action, in the later study, we need to focus on the group action on some factor space. So it is necessary to consider the classification of an isometric action on a Gromov hyperbolic space. And by Gromov, an unbounded isometric group action on a hyperbolic space can be classified into 4 types. The first is holocyclic. It means that there is no loxodromic element. Every group element acts on the space like elliptically or parabolically. And the second type is linear. It means that there is a loxodromic element, and any 2 loxodromic elements have the same fixed points in the boundary. And the third type is focal. It means that it has a loxodromic element, and any 2 loxodromic elements have 1 common fixed point in the boundary, and it is not linear. It's not linear. And the last is of general type. General type, it contains all the remaining cases. And in particular, it has 2 loxodromic elements with disjoint fixed points in the boundary. And another notation that I want to mention is the displacement. It's defined for a group action. For a set S of the group G, the displacement of the set of the subset at some point X is defined like this. Is defined to be the maximal translation length of S on X. And the displacement of the subset S on the whole space X is defined to be the infimum over all displacements of S on some point X in the big X. Okay, the last and most important conception that I want to mention is the shadowing property. We define the shadowing property also for the group action. For group action, we take a generating set F of G and a base point O in the space X. We say that the K graph has a path system P consisting of some uniform coarsely geodesics. I want to mention that the path system may not contain all the coarsely geodesics. Is determined by us. It's a collection of preferred uniform coarsely geodesics, such that for any two group elements, they are connected by some paths in P, and any subpaths of gamma in P are still contained in P. And the most important property is the third item. It says that for any gamma in P, the image path gamma tilde in the space is a uniform unparameterized coarsely geodesic, and the image path is given by the orbit map. And here is a remark. It says that if the X is a space, if the space is a hyperbolic space, then the shadowing property can imply a co-bounded action. And that's the only assumption that we add. And now I'm going to introduce our main result. This result is not the same as in our paper. It's not complete, but I think it's enough here. Suppose that a finitely generated group G admits a proper product action on finite hyperbolic spaces, and the only assumption that we add is that with shadowing property on each factor, then our conclusion is that G has locally uniform exponential growth. Notice that locally uniform exponential growth is a stronger conception than uniform exponential growth. It says that for any finitely generated subgroup, if it's not virtually abelian, then it has uniform exponential growth. So clearly, you can imagine that it is much stronger than uniform exponential growth of the whole group G, right? Okay. Then how to prove our result? The proof ideal is also a general method for showing a locally uniform exponential growth. The first step is always to generate is there any question? Okay. The first step is always to generate a quick logarithmic element G on some factor space for any sufficiently large subset. Notice another notice is that if you just want to show uniform exponential growth, then you can replace the sufficiently large subset by a sufficiently large ball in the Kelly graph. But if you want to show locally uniform exponential growth, then the large ball is not enough because you need to take any subgroup, right? So you should show the logarithmic element for any sufficiently large subset of G. Okay, this is the first step. And the second step is always to generate another quick logarithmic element F on the same factor space, which is independent of G. And the last step is to apply the lemma to get a to get a free subsemigroup, and then we can get the locally uniform exponential growth. Okay, is there any question? And then I'm going to use our proof more a little detailed, not very detailed, but a little detailed. And first, we come to the step one. We want to generate a quick taxonomic element, right, on some factor for any sufficiently large set. And our setup is that suppose G admits a proper product action on finite hyperbolic spaces X with shadowing property on each factor. And the first thing I want to note is that you can imagine that as the product action is proper. So for any sufficiently large subset S of G, you can get a large displacement on the whole space because the product action is proper. So you can imagine that. But okay, the second thing is that we want to transfer the large displacement on the whole space to get a large displacement on some factor space. Note the difference. It's not very easy. So here we use the assumption shadowing property guarantees that large displacement on the whole space will imply large displacement on some factor space. Here is the only way that we use our assumption shadowing property. And if we get a large displacement on some factor space, we can apply the following lemma to get a quick element. The following lemma is very useful in our paper.
I can't hear you. I can't.
Okay, I'm sorry.
Yeah.
Maybe there is something wrong with my earphone. Okay. As you get a large displacement on the space, then we can apply the lemma, the following lemma to get a quick logarithmic element on xi. This lemma is very useful in our paper, and I think it must be very useful in some other related works. Okay, it says that for any finite subset of isometries of a hyperbolic space X, if the displacement of this subset is bigger than 30 delta, then there is a logarithmic element that can be expressed by at most 2 letters in the subset. This is what the lemma says. Okay, so follow the step 1, we can get a quick logarithmic element. And now we come to step 2. We want to generate another independent logarithmic element right now. Record the classification of isometric actions on normal hyperbolic space. As we have already one logarithmic element, then the group action cannot be holocyclic. So the other 3 actions, linear, focal, and of general type. Note that focal and of general type actions both have independent logarithmic elements, but linear action says that any logarithmic elements fix the same points in the boundary. So if you want to generate an independent logarithmic element, it is equivalent to show that the action of the group on the factor space is not linear. And we give a definition of the commutator subset here. For any 2 subsets HQ in G, we denote CHQ as the commutator subset consisting of all commutators between H and Q. Okay, this is just a definition. And there are some facts that actually they are all lemmas in our paper. The first fact is that suppose a linear action is orientable. Orientable means that no group elements will exchange the 2 limit points of this linear action. So suppose a linear action is orientable, then the orbit of the largest commutator subset on the space is bounded. It also implies that the displacement of the largest commutator subset on the space is finite. Okay, the second fact is a group theoretical result. It says that let G be a non-virtually abelian group. Then there exists a constant small c independent of any generating set, such that the commutator subset of the ball of radius n has a cardinality growing at least linearly, right? Cn grows at least linearly. With these two facts, we can introduce how to get the step 2. At first, you choose any non-virtually abelian subgroup H, and choose any finite generating set S of H, and you consider a large enough n, then the commutator subset of the ball of radius n is sufficiently large, right? By the lemma 6. Then the commutator subset is sufficiently large. And notice that this commutator set still is contained in the ball of radius 4n. So since this commutator subset is large enough, then we can use step 1 again. There exists a loxodromic element in a large ball of radius 8n on some vector space xi, and step 1 is that the displacement of the commutator subset on the vector space xi is also very large. So we can get that the subgroup H on the vector space the action cannot be arrangable linear. Otherwise, it will contradict with the first fact. The first fact says that arrangable linear action will imply a bounded displacement. Until now, we can get two independent elements, and finally, we can apply the following lemma to get the locally uniform growth of G. This lemma says that for any let X be a hyperbolic space. Suppose
Sorry, I can't hear you.
Okay.
Yeah, I can hear you now.
Maybe I can hear now. Okay. Sorry. Step 2, you hear the step 2, right? So so in step 2 we get the two independent logistic elements now. Then we can apply the following proposition to get the local uniform exponential growth. The proposition says that let X be a dot hyperbolic space. Suppose G and H are two logistic elements, are two independent logistic elements. If tau G and tau H is bigger than 10,000 delta, then some pair in the subset will generate a free sum group. Here, tau G means the stable translation length of G. It is almost the same as the displacement of G. They have a error. They have an error bounded by 16 delta. So tau G is, you can imagine that tau G is almost the same as the displacement of G. And step 2 says that displacement of both two logistic elements are still very large. No, this may be implied by step 1. Yeah, lemma 5 implies that the logistic element has almost the same displacement with the displacement of the subset. So if the displacement of the commutator subset is very large, then lemma 5 can imply that the displacement of the logistic G and H will be very large. Then we can apply the proposition to get a free sum group, and then we can get the local uniform exponential growth. That's the main proof. Okay. And one corollary is that a hierarchically hyperbolic group with a BBF coloring, then G has locally uniform exponential growth. This kind of groups, including Epping class groups. So, and for more results and details, people can see our paper. Okay, that's all. Thank you.
Thank you, Renxing. Any questions for Renxing? So it is difficult to show like something satisfies the shadowing property. Or
Shadowing property.
yeah.
We use shadowing property in this step. It transfer the large displacement on the whole space to large displacement on the vector space.
Mm-hmm.
Yes. And the shadowing property excludes this situation that any finitely generated group will act properly on its orbital of its K-graph. The property will exclude this situation.
Any other questions to Renxing? If not, thanks to Renxing one more time. Thank you.
Thank you.